Hi friends. So last we left off, I was demonstrating how the transmit and receive functions of this modem and the transmitter all work. And you will recall, if you saw the previous video, that when I was transmitting, there was between characters, there were no audio, there was no audio whatsoever. And this really apparently is a problem to conduct RIDI over the air with having a QSO with somebody else. They really require a constant mark tone in between characters. And so, we were trying to figure out how we're going to do this. And if you'll recall back, the whole reason this all happened was because this Harris modem requires an RS-232 signal called request to send RTS to be asserted before it can start generating tones. And I had been trying to avoid producing a physical switch from this operating position over to the modem to flip that RTS signal to get the whole system in transmit mode. I was sort of trying to keep this as automated and as light touch as possible. And so, in order to do that, the black box communications adapter was used to assert the RTS signal to the modem whenever it saw data coming in from the computer. And this was all well and good, except for the fact that the RTS was deasserted between characters, as there's no data between characters, and therefore the audio stopped between characters. And this is a problem. So in this video, we're going to look at a circuit that was co-developed by myself and my dear friend Peter KB2VTL, and to be placed in line with the RTS signal, the request to send signal, so that it will switch quickly when I go to from receive to transmit, but when it goes from transmit to receive, it will switch slowly. And the reason being, the slower it switches, the more time it will give that RTS signal between characters and maintain the mark condition. So let's just review what things sounded like before. You see, there is silence between the characters. And that is what's not good for RIDI, over the air, because the receiving side will either will start displaying garbage. What you really want is to have a constant mark tone in between characters. All right, so the whole project here is to create a circuit that will, when I go to transmit, it will as quickly as possible assert the RTS line and get the modem operating. And the modem, when the modem starts generating audio, the transmitter will switch from receive to transmit. That's so that we want that to be delay as little as possible. However, when I stop typing, I want there to be as long a delay as possible on this RTS signal to give RTS more time between my characters as I type to keep the mark frequency, the mark tone steady. And so this is the circuit that we came up with. Again, this is with a lot of help, mostly entirely from KB2VTL. And then this is a new attempt at playing it with things in KiCad or KiCad. I think it's KiCad. As you can see, I laid the circuit out. But really, the benefit of one of the many benefits of KiCad is you can do a spice simulation. So that's what we did. But in order to do a spice simulation, we had to add a few extra components. So what you see we've added on the left is a voltage source, and that voltage source is designed to pulse to show a positive 10 volts or a negative 10 volts, indicating that the computer has either asserted RTS or released RTS. There's a 300 ohm resistor which is designed to simulate the source impedance of this line. Now, most of these RS-232 signals are coming from either a 1488 or 1489 a pair. These are the most common pair for RS-232 signals, the line drivers. 1488 and 89, I forget which is the receiver and which is the transmitter, which is the receiver, which is the driver. But they have a source impedance of about 300 ohms, and that will affect the timing of the circuit. As you see, you have R's and C's, you get RC constants, etc. And then on the right, this is RTS out to the modem, and the input of the line receiver is spec'd out at about 5K ohms. This has less of an impact on the overall circuit timing, but nonetheless, we wanted to put it in there so it could be represented in the simulation. So let's take a look at the results of the simulation. So this is the output of the simulation. Let's look this over. So the red signal is RTS. Initially, it is in a transmit mode, and it's high. And then the RTS from the computer drops to receive mode instantly. However, the blue line is the output RTS output line to the modem. And what you can see is that it takes some time to drop. And however, though, at about 15 seconds again, it starts back, I go back into transmit mode. So although it's not perfectly square and it's not perfectly, the transients aren't square, it's still okay because these line drivers and line receivers have thresholds above which and below which they consider these to be sort of ones and zeros. Just take a look. Let's take a look at the next slide. So what you can see here is if you look at the yellow horizontal line, that is set at -3 volts, and the line receiver in the modem will consider anything below -3 volts as a let's just call it a binary 0. And likewise, in order to have a binary 1, it has to be over +3 volts. We'll look at that soon. So what you're seeing here is that while the blue line is sloping down, RTS is remaining on up until it crosses the yellow line. And you can see in this particular simulation, it starts at about 5 seconds into the simulation when when I'm stopped typing essentially on the keyboard. And by the time RTS shuts off to the modem, it is about 10 seconds. So this circuit is giving me about 5 seconds between characters that it'll continue to keep the RTS on and therefore continue to keep the mark signal on. Okay, so there's no free lunch. We're not using any active components here. We could have used a 555 timer circuit or other methods, but we're not. I didn't want to have to start bringing power into this circuit, and I just wanted a simple set of discrete components that I could put in line on the RTS signal on the RS-232 port and have it do its thing. So what you can see here again is that the RTS takes this time. You can see this longer, lower ellipse here. It takes its time shutting off. And then when we go into transmit mode, you can see the top yellow line indicates when that transition is considered on. And if you can see the small yellow circle, it's not instantaneous. So it turns on, the computer turns RTS on the red line at about 15 seconds in the simulation. The blue line doesn't actually cross over the 3 volt level until about 16 seconds or 1 second later. And this will explain a little bit why there actually is a little delay on transmit, but certainly acceptable for our purposes. So overall, the simulation indicates that the circuit is definitely doing its job. We did a lot of playing around with components and seeing if we optimize and maybe another diode here or there to clean things up. But really, this is the most optimal solution. And let's see how it looks. And here is the circuit laid out. There's very little of it on this little breadboard here. See if you can see. There's really not much to it. Let's get around to this side maybe. Yeah, it's just a couple of small signal diodes, a resistor in there somewhere, if you can see it, and these two caps, big caps to ground, just like the diagram described. And here we've got in coming from essentially the computer, and this is what's asserting the RTS line to the modem. The RTS line then goes through this circuitry to delay it being turned off. It goes on fairly quickly, but is a delay turning it off. And then up here is the output of the circuit, which goes to the modem. And the modem is the thing that we need to control the RTS for the purpose of getting the mark signal going or not. The rest of this old Heathkit breadboard is not being used. In fact, there's not even power necessary. It's not plugged in at all, as you can see by the as you saw by the diagram. One thing I did want to point out is to make testing easier and to make demonstrating the function of the circuit easier. I made a little extra wire here, which puts these two capacitors to ground. Without it, the circuit behaves as if the circuit was completely bypassed, and meaning the old way of the thing working. And then when I put this to ground, it will start behaving with the new circuitry in the mix. So again, now let's try it with the circuit in place. All right, so I added the jumper onto the circuit that we showed earlier. And one thing you will notice if you remember from the simulation, it does take a small amount of time, I didn't actually calculate it, for the RTS to get asserted on transmit. And so what you'll notice is I do miss a few characters while typing. So, but I think that's okay. I think practically I could just use the space bar 5 or 6 times and then a carriage return line feed and go. So let's see what happens. I'm going to add 5 space bars. So now you can hear. Whoops, let's try that again. So now you can hear, and let's type. So what you'll notice is a constant mark signal in between my characters. And what happens now is when I stop, well, it's buffered. So I have now time. If my typing is slow, you can see that I have a mark space in between the characters. And then eventually, when I'm totally done, it'll stop, and then the transmitter will go into receive immediately because of the Vox circuitry. So I'm very happy with how this worked out. It's going to take a little testing, a little work in the real world. But it looks like it will have the desired effect. All right, I wanted to do one final demonstration, which is putting everything together, which includes using the terminal in addition to this new RTS delay circuit that gives me mark signal between characters, and the fact that I've got the Vox, the voice operated transmit setting on the exciter and the transmitter set. And so now you can see how the whole thing will work without any manual intervention to go between receive and transmit. So I've got my receiver. You can't really see it too well, but I'm gonna take it off. I'm gonna put the speaker on so you can hear. It's just the idea is just to use it to show when the transmitter is switching from transmit to receive. It's not actually receiving anything. So hopefully you can hear now that it's just noise. It's just noise. And again, the noise will turn off when it goes into transmit mode because of the muting function of this system. And so let's begin. So we're gonna. Oops, hold on. Let's turn the transmitter on. You could probably hear the fans. And let's get started. So you can hear, again, I now have mark condition between characters. And once I stop typing, you'll hear the mark space will stop, and then the receiver will go back to producing noise. So, and I didn't have to do anything. I didn't touch anything. And there, the receiver switches back because of Vox. Now, ultimately, let me turn this off. Ultimately, the plan is to reduce the hang time of the Vox. So that way, as soon as I'm done typing and we drop the mark signal, it will switch right back over to receive. Right now, it's sort of like 3+ seconds when the mark signal is dropped to when it switches back to receive. But this is adjustable. This is an adjustable setting in the exciter, and I'm going to do that. So anyway, now you get an idea how the whole thing works. Completely automated, doesn't require throwing any switches to go from receive to transmit. It all just kind of works. The last step in this project, of course, is going to be to take that circuit that's been breadboarded and soldered onto a little sort of a perforation board, and stick it into the RS-232 lines permanently. Right now, it's just sitting on the breadboard. But that's it. Very exciting, and thanks for your time. All right, and thanks again to Peter, KB2 VTL, for help on designing the circuit. Have a good night.